So one of the ways that we can use these Maclaurin series that we're working with is to approximate values of trig or other transcendental functions. So if I have this sine of x, we can approximate, but it is going to be a very accurate value for a trig function. Now we use this because trig functions lack finite algebraic formulas, right? But power series are going to be our next best thing. So we're going to use a Maclaurin series for sine of x to approximate sine of 1. But then immediately this question goes into so that the error in your approximation is less than 1/1000th. Now we're going to do this without using our calculator, and we have to have some sort of justification. So the idea is if I'm going to try to find sine of 1, I know I'm going to be putting a 1 in to this expression, but how many terms do I use? Well, this idea of this error being less than 1/1000th immediately takes me back to error understanding that I already have. Y'all, sine of x as a Maclaurin series is a alternating sine series that is decreasing in magnitude to 0. Alternating series error bound applies to this. So if I'm going to do sine of 1, I'm going to take a 1, this is an approximation. So I'm going to take a 1 and I'm going to plug it in everywhere x is. And I'm assuming I'm not going to need more than 4 terms. I might need more than 4 terms. But let's talk about that alternating series error bound. So I'm going to go ahead and simplify this a little bit. So this is 1 minus 1/6 plus 5 factorial is 120. And then if you don't know 7 factorial, which I'm assuming most of you don't off the top of your head, and I'm not using a calculator for this, you might just do 7 times 6 times 5 factorial, right? We've already analyzed 5 factorial as 120. So I might need another term, but remember, alternating series error bound says that the error, if I do 2 terms, can't be bigger than this, right? Well, this is bigger than 1/1000th, so I'm going to keep going. This value, I know this is 42 times 120. Even if I don't know that number, I know that this fraction is less than 1/1000th. So this is less than 1/1000th, which means I'm going to use a partial sum with 3 terms to do my estimation to guarantee that my error is less than 1/1000th. So sine of 1 is going to be approximated by a sum with 3 terms. We're going to do 1 minus 1/6 plus 1 over 120. Obviously, we can leave it like this unless we're trying to reduce on the for like multiple choice, but we can leave it like that if it's an FRQ. It's not bad to reduce. The 1/6 is just 20 over 120. So this becomes 101 over 120. So that is my approximation for sine of 1. And because I used 3 terms for my sum, this is a remainder of that partial sum is less than 1 over 7 factorial. You can write this as 42 times 120. You can write it as 7 times 6 times 5 factorial, right? It's all of those things, okay, whatever you want to do. But that is less than 1/1000th by alternating series error bound. Now your calculator is actually using Taylor series to approximate sine of 1, but it's using a bunch of terms. So that information is actually proprietary, so we don't know exactly how TI has programmed this. But really, this is the only way to get these values. I just don't know how many terms they used. But if you put sine of 1 into your calculator, and then you subtract the approximation, you're actually going to get a number in scientific notation, which means it's really small. But you get 0.0001957. Y'all, I only used 3 terms for my approximation of sine of 1, and it is within 1/10,000th of the accurate answer. Obviously, that's a little bit bigger than that, but it's within 2/10,000ths of the actual value of sine of 1. Yo, that's pretty good, considering the skills that I have, considering that I only use 3 terms. So when we didn't have calculators, right, we didn't have computers in our hand, and you used 4 or 5 or 6 or 7 or 8 terms to approximate sine of 1, you were getting a very, very accurate answer for that.